Okay, we're gonna look at kinetics. So you guys have a packet to fill in as we go along. The packet was made at a different time from this, so some of the things are going to be out of order a little bit, and that's okay. I'll tell you when to jump around. So we just finished looking at thermodynamics, and thermodynamics tells us if a reaction is going to happen. Basically, things become more stable. So we use thermodynamics to tell if a reaction is product or reactant favored. So will you proceed to make more products, or will you keep your reactants? But it doesn't tell us how fast a reaction occurs. Kinetics is how fast something's going to happen. So kinetics is the study of reaction rates and their relation to the way the reaction proceeds. In other words, the mechanism. So the mechanism is looking at almost like Hess's law, how we see reactions don't always just happen in one step where you have your two reactants and they react and you make one product. Quite often you'll have one change in your first step and then a second step will occur, and overall the reactants turn to the products, but they made a series of changes to get there. That's called the mechanism. So the mechanism is how the reaction actually occurs. So what we do is, in kinetics, we're studying how different reactants affect how fast a reaction occurs, and basically like what's going to affect the rate. And from that we get the mechanism, which is our idea of how does the reaction actually occur? What are the steps that are actually happening? So from this you guys should just have the first part, define kinetics. Okay, this is actually the collision theory, the 3 parts of collision theory. So next to last page. So the 3 parts of collision theory is saying, well, the first part, in order to have a reaction, particles must collide. That makes sense. If the 2 reactants don't come into contact with each other, they're not going to react. Secondly, collisions must overcome activation energy. So they have to collide hard enough to actually form a reaction. And that's going to be, we often see how we have these energy diagrams where we say these are our reactants, and then those are our products. So this is the stability of the energy that our reactants have. This is the energy that our products have. To go from here to here, if this is energy, this is going to be our activation energy. This is how hard the reactants have to collide in order to react. And some of that could be, it's making your reactants less stable, so they're more likely to go through the change of reacting. So you could have initial bonds in your reactants, and this collision could break some initial bonds in your reactants, make them unstable, make your reactants less stable, so they'll form a new arrangement, which is going to be your products. So number 2, collisions must overcome activation energy. And 3, collisions have to have the right orientation. I like to think of this as, if I have this strange looking molecule, it's not a molecule, this is just my picture to represent a funky molecule that's really big and only has one spot that's going to be reactive. So if this is one reactant and this is one reactant, we could say the only way this thing actually reacts is if the collision occurs with this going into that, right? That if this particle hits over here, there's no reaction, or if this particle hits over here, there's no reaction. So you could think of it as reactive parts of a molecule have to come in contact. So the particles have to collide, they have to collide hard enough to overcome activation energy, and they have to have the correct orientation to react. So now we're back to the first page. Sorry, jumps around. Defining rate of reaction. So reaction rate is the change in concentration over time. If you're looking at a reactant, as your reaction occurs, you have less and less of that reactant. So you have this negative change, right? So if you're looking at a reactant, it's negative change in concentration over time. If you're looking at a product, you're making products. So, and the reason you're looking at change of concentration is I have this reaction I'm carrying out, and I want to know, how fast am I actually making stuff? So that's why I'm saying, well, how fast is the reactant disappearing? How fast is the product appearing? So there's 3 types of rates that are often used. The initial rate is going to be the rate at the very beginning of your reaction. When you first mix the reactants together, how fast is the reaction occurring? The average rate is going to be the rate over the entire time. So the difference between that would be, initially I would say, well, how fast are things happening right here? And I would draw a tangent to this one point of the curve and be like, that's about the slope. And I would So you look at the slope, so the change in the y over the change in the x, and that'll give you your slope, or how fast the reaction is happening right here. The average rate is going to be overall how fast was this happening. So you'd say, well, here's my first point, here's my second point, my last point, and I just go ahead and draw a line connecting those two, and I say, on average, throughout the reaction, how fast was this happening? So I see how much concentration changed over how much time, and I divide change in concentration over time to get the slope of this line, and that tells me on average how fast the reaction was occurring. What we like about average rate is that it's just taking 2 points. What we don't like about it is, well, first of all, you have to have a way to measure that final concentration. Your initial we know. And the second thing is you can see the rate's happening really fast and it happens slower with time. This average rate doesn't give you a lot of information. At some point, you were going this rate, but in the beginning you were going faster, at the end you were going slower. This just tells you on average. So instantaneous rate would be if you chose any point on your curve. So I've got this graph which is showing concentration versus time of a reactant, and it's decreasing. Sorry, I didn't explain that first. If I looked at instantaneous rate, I would take any point on the curve and I would draw a tangent line at that point, and I would say what is the change in concentration over the change in time, and that would be the instantaneous rate. So the instantaneous rate can tell you the rate at any point in time during the reaction. How fast is it happening now? What about now? The hard thing with the difficult thing with instantaneous rate is you have to have a way to measure your concentration as the reaction's occurring. So you imagine if you mix two reactants, before you mix them, you know what you have. So that part's easy. But as the reaction's occurring, you have to figure out how much has reacted to know what your concentration is now. So you need a way to measure your concentrations as the reaction occurs, and that's difficult. We often use this one because we do know the initial rates. So we're just measuring that, what do we have right now. So those are our 3 rates. Oh, and I've got time to do a little more. So let's see, our next thing we have factors that affect rate. Great, so concentrations. We could see that the rate happened very fast, or the reaction happened quickly at first, and the rate was slowing down because that tangent line is getting flatter and flatter. It's because when you have high concentrations, there's more collisions of particles. And as those particles collide, they turn into products. So your concentration of your reactants goes down as the reaction's occurring, so you have fewer and fewer particles to collide. Fewer collisions, fewer reactions, it's a slower rate. The physical state is getting at, do you have solid, do you have liquid, do you have gas? This matters because if you have a gaseous state, you have more particles that are moving around, there's more surface area, they're more likely to collide. Even if you had a ground up solid versus a whole tablet of something. You know, if you're trying to dissolve a solid, it's easier if you grind up the solid first and you're increasing the surface area. So if there's more surface area, there's more places where particles can collide, more places where reactants can meet and collide and react. Temperature, if you increase temperature, particles move faster, and as they move faster, we know we're going to have more collisions because they're running into each other more often, and these collisions are going to be harder. This is even more important. The collisions are going to be hard enough to overcome the activation energy, make your reactants unstable, so they're going to react. And a catalyst, what a catalyst does, these are all ways that you can affect rate. If you increase the concentration, rate happens faster. If you increase the surface area by having a gas or a ground up solid, you increase the rate. If you increase the temperature, particles move faster, they collide more often and harder, you increase the rate. If you add a catalyst, you also increase the rate. And it's because if you add a catalyst, you lower the activation energy. You lower activation energy. And it's by providing an alternative pathway, which we'll talk about more.